Hello, in this video we're going to continue with part 2 of our probability notes. You can follow along with your chapter 4 probability guided notes. We're going to pick up on page 3 right where we left off with example 4, where we had a number set of the integers from 1 to 25 and we were finding certain probabilities. One of the probabilities we found in part B was the probability of an event that a number was less than 10 and also greater than 20. We determined that there were no numbers that were less than 10 and greater than 20. So the probability of event B occurring was 0. Another probability we found in part C was the probability of event C that a number less than 26 was drawn. Since our set was numbers 1 through 25, no matter what number we drew, it would be less than 26. So the probability of drawing a number less than 26 was 1. We call that a certain event, an event that is certain to occur. It has a probability of 1. Now, event B of drawing a number that is less than 10 and also greater than 20, that would be impossible. So an event that is impossible has a probability of 0. Other examples of an impossible event, well, if today is Tuesday, it's impossible that tomorrow is Monday, because Tuesday comes after Monday. If today is Tuesday, then the probability that tomorrow is Monday equals 0. Remember, a certain event is an event with probability is 1, certain to occur. If today is Tuesday, then the probability that tomorrow is Wednesday is 1. If today is Tuesday, then tomorrow is definitely Wednesday. Another certain event is that on any given day, the sun will rise. The probability of the sun rising is 1, even if we don't see it. If it's behind the clouds, it still rose. This next section of your notes, you'll want to put a box around or star because it is an important reference for you. The important principles of notation for probability. This is a good summary of the things we're going to learn about probability. The probability of an event is a fraction or decimal number between 0 and 1 inclusive. That means it can be any number from 0 to 1, including 0 or 1. Now, if you're doing calculations and you get a probability that's negative or a probability that's greater than 1, that means you've made a mistake. So you can use this idea to judge your answers and check your work. The probability of an event is equal to the sum of probabilities of the disjoint outcomes making up the event. Next, we have the probability of an impossible event is 0. And the probability of an event that's certain to occur is 1. We just went over those. When we see P, open parentheses, A, close parentheses, we read that as the probability of an event A. When we see P, open parentheses, A with a line over it, close parentheses, that means the probability that A does not occur. You might hear that read as probability of not A or probability of A complement. Not complement, but complement with an E there. And then finally we have if A and B are any events, then the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So this tells us or you could say union, and this symbol tells us and, or you could say intersect. I will be using and or when I see these symbols in this section. Don't worry, we're going to do a number of examples to practice this formula. Before we go any further, I'll let you know that in probability, there happens to be a lot of problems that have to do with a standard deck of playing cards. They make it easy for us to find probabilities just the setup of a standard deck of playing cards. So if you're not familiar with a deck of playing cards, I have a reference right here. A deck of playing cards has 52 cards. There's 26 red cards and 26 black cards in the deck. So half are red, half are black. In the red suits, we have hearts. So there's 13 cards that are hearts and 13 cards that are diamonds. So hearts and diamonds. In the black suits, we have spades and we have clubs. So there's 13 cards in each suit. Now, the cards in each suit include an ace, which just has an A on it, or you might see a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have a jack, which will just be denoted by a J, queen, Q, king, K. So when I'm referring to any of those, I'll just use the one letter in my work, and for ace, I'll use an A. An ace is not considered a face card. Jack, king, and queen are considered face cards. You can use this reference in the blue box throughout the unit. Let's do one example now. Example 5. If we draw a card at random from an ordinary deck of playing cards, what's the probability that the card is an ace? So my notation will be probability of an ace, and you always want to include your notation. We have to think how many aces are in the deck, because that'll be our numerator of our fraction. Well, there are 4 suits, and each suit has 1 ace, so there are 4 aces in the deck out of a total of 52 cards. We can reduce that fraction by dividing the numerator and the denominator each by 4, and we'll get 1 out of 13 is our probability. Make sure you express fractional answers as a reduced fraction. If you give a decimal answer, round to 3 decimal places. Next example, part B. What's the probability that a card is an ace or a queen? So the probability of an ace or a queen. This is where we use that formula from the previous page. So we'll take the probability of an ace and we'll add it to the probability that we have a queen. But one thing we want to think about is, are there any aces that are also queens? So that's where we're going to subtract what I like to call the overlap, or we learned the intersection of ace and queen. So we're going to subtract the probability that something is an ace and a queen. So the probability of an ace we already found is 1 out of 13, but I'm going to use the unreduced answer here in my calculations because I know for adding and subtracting fractions I need a common denominator. So there are 4 aces in the deck. We also know there are 4 queens out of 52 cards. Are there any cards that are both aces and queens at the same time? No. So the probability of that would be 0. So we have 52 plus 4 out of 52 minus 0 out of 52, giving me 8 out of 52, or simply 2 out of 13. Even though ace and queen didn't have an intersection, they're disjoint events, so you could just add them up. I always like to encourage students to think about this intersection and whether they need to subtract it or not for any problem, because then you won't forget when the time comes that you do need to use it. As a reminder, mutually exclusive events, when we do have those events that are mutually exclusive, they have no elements in common. That means that the event A and event B are an empty set. So the event of queen and the event of ace was an empty set. So the probability of their intersection is 0. For example, here we have a spinning wheel to our right. Now the sample space is the numbers 0 through 9. Those are all the numbers on the different sections of the spinning wheel. We have event A, which is spinning a 0 through 4. So we can mark off 0 through 4 in yellow. And then we have event B, which is getting a 5 or 7. So let's mark off 5 and 7 in green. As you can see, if you spin something yellow, you can't spin something green. None of the yellow numbers are also green numbers. So none of the events in A are also in B. So we say that the events are mutually exclusive. For mutually exclusive events, the probability of those events A and B, probability of A or B, equals the probability of A plus the probability of B. You can just add them up. In this case, the probability of A would be 5 out of 10, because there are 5 numbers highlighted in yellow out of the 10 numbers on the wheel. The probability of B is 2 out of 10. So when we add this together, we get the probability of spinning something from set A or set B would be 7 out of 10. In words, we just found the probability of the union of events. So the probability of union of events such that any two are mutually exclusive is just the sum of the probabilities of those events. Let's talk more about complementary events. Two mutually exclusive events whose union is the sample space are complementary events, like weekday and weekend. If event A is an event and A with a line over it is its complement, then the probability of A plus the probability of A complement equals 1. We can manipulate that formula to get the probability of A equals 1 minus probability of A complement, and probability of A complement equals 1 minus the probability of A. You might see A complement listed as not A. We consider the days of the week and we have the sample space of weekend and weekday. If I pick a day of the week at random, the probability that I pick a weekend day would be 2 out of 7, because Saturday and Sunday are the only weekend days. Whereas if I pick a day of the week that's a weekday, not a weekend day, we have a probability of 5 out of 7. When I add 2/7 plus 5/7, I get 1. So the sample space is made up of weekend and weekday, and their probabilities add up to 1. They're complementary. If I take 1 minus 5/7, I get 2/7. If you remember from part 1 of our video, we looked at a skydiving question. Here we have, in a recent year, there were 3 million skydiving jumps and 21 of them resulted in death. Find the probability of not dying. So before we found the probability of dying, our sample space here would be made up of either dying when you jump or not dying when you jump. So what we can do is we can use complements to find our probability of not dying. We knew the probability of dying was 21 over 3 million. So we can say that the probability of not dying would be 1 minus 21 over 3 million, or 1 minus 0.000007. That gives us 0.9999993. So chances are, if you skydive, you're going to live. Last complementary events example, we're going to consider the event A of numbers 2 and 4, tossing a 2 or 4 on a standard die. So a die is a cube. On each side of it, it has one of the numbers 1 through 6. The complement of A is the set A complement, with a line over it, of 1, 3, 5, and 6. So the probability of A would be 2 out of 6, or 1/3, because there are 2 events, 2 and 4, that we're looking for, right, out of 6 total events. The probability of not A, we can find 2 different ways. We can use complements. We can say 1 minus the probability of A, or 1 minus 1/3 equals 2/3. So 2/3 is the probability of getting a number other than 2 or 4. But we can also consider the probability of getting another number other than 2 or 4 will be getting 1, 3, 5, and 6. So there are 4 options there out of a total 6, which also reduces to 2/3. So those are 2 ways to find the answer. One using complements, the other does not.